I have no idea what level of experience people are here, so I'm going to ask some quick questions to kind of see which parts I should focus on. Who here knows what an integrated circuit is? Hopefully, okay. Who here has made their own integrated circuit? Okay, we have a couple of people who've done that. Who here has played with a microcontroller like Arduino or something along those lines? Okay. Who here knows what a silicon foundry is? Okay. What about a PDK? Okay. A bit more technical than the average audience I've given this talk to, which I somewhat expected given that the foundry I'm working with is based here in Singapore. So I guess how I normally start this talk is go, so you want to make a silicon chip. Well, the terminology we generally use is tape out a silicon chip. And traditionally, to do designing silicon, you basically have to sign your life away and sign multiple NDAs with different groups. You have to sign an NDA with your silicon foundry. You have to sign an NDA with a tooling vendor. You have to sign an NDA with a person supplying you with proprietary IP. And that basically makes it very hard to get started as an individual who hasn't, got a company that can even sign NDAs in the first place. As well, you may be familiar with some of these type of things where, it seems like you need billions of dollars to do things in this space. I've just come from the US, and there they spent $52 billion on a thing called the CHIPS Act. The latest TSMC foundry was quite expensive. Just one of the ASML machines used to make a chip is about $380 million per machine, and you need many of them in a foundry. And this is kind of a graph that at like 5 nanometers, they're estimating you need about $500 million to make a chip. So if you believe all that, then you don't get to make a chip really, unless you go and work for a mega corporation and have to deal with all that. So when you're making a chip, really there are kind of 3 parts to making the chip. You need tooling, you need basically the code and the libraries, and then you need it manufacturing. And this is something that generally software people don't have to deal with. In software, once you've made it, you can just kind of ship it. Sadly, with real silicon, you actually have to get it made somewhere. It turns out there's actually a long history of openness in the tools used to make chips. Things like Spice and Magic originated as open, and Magic is so old, it predates terms like open source, and it's a year older than I am. And so then also we've got things like Yosis and XPNR, which were very active in the 2015s. And then this guy called Andreas Olsson also did this big $100 million DARPA initiative, which kind of supercharged these tools. And so all of a sudden, you had tooling that enabled you to create a chip that was accessible, that you can just download off the internet without having to sign NDAs. If you're a software person, you can think of this as like your compilers, your debuggers, all that type of stuff. Then, if you're a software person, think standard library and operating system. That's your code and libraries. There's also a pretty long history of openness here. Open cores comes from like 1999, and OpenRISC comes from 2000. That was the first attempt at making a fully open RISC ISA. You may have heard of something called RISC-V, which I guess is now 15 years old. That's been exploding in popularity at the moment, and that's your CPU core. And there's a whole bunch of other groups that have been doing cores, which allows you to have the building blocks you need to make a chip. Oops. But when I kind of entered this space in 2019, there was a big thing missing, which was basically PDKs, which are the process development kits. They're all the rules that let you know if you're making something that the foundry can actually build, and things like MPWs. I don't know about you, but buying silicon can be quite expensive as opposed to like shipping something over the internet. And so I really believed that we needed to improve this area, because imagine trying to write a compiler without ever being able to run the output of that code. That would be almost impossible. And also imagine being able to develop libraries and then never see how they're actually implemented. You'd be very hamstrung. Luckily, at the time, I was at Google, and using Google's resources, I was able to convince this foundry in Singapore, not in Singapore, in the US, called Skywater, to release basically what was the first 130 nanometer PDK. So 130 nanometers is about 2000 era technology. It still exists, and it's still used heavily for microcontroller level stuff like that Arduino style chip. Then based off the success of that, I worked with a company called Global Foundries to release a second PDK called GF180 MCU. And it turns out GF180 MCU is made in Singapore out at Woodlands. And then independently of the work I was doing at Google, this group called IHP released a PDK for their own foundry. And so this was actually a proof that what we were doing was starting to make an impact, because it was the foundry itself releasing the PDK. And so these first two were released by Google. And this one was released by their foundries. And there's a bunch of other ones that are kind of happening. But like just having the rules is hard to do anything without actually manufacturing it. So Google even basically provided free manufacturing on these process technologies if your designs were open source. And through that, they sent 476 devices off to be manufactured at Skywater, of the 900-ish or like 1,000-ish designs that were submitted. And for the Global Foundries one, they got 80 manufactured out of the 200-ish so designs that were submitted. And one of the cool things was, from this came a project called Tiny Tapeout. And so Google had basically taken a manufacturing run and divided it by 40, which allowed 40 people to do chips. Tiny Tapeout then said, well, what happens if we divide this even further? And it turns out that if you take a number like $10,000 and you divide it by 200, it only costs you $50 to do a tape out. And so Tiny Tapeout's been very successful in enabling anyone who has a web browser, a couple of hours, and 50 to 200-ish bucks to effectively tape out their own silicon chip. And so today, you can go to Tiny Tapeout and create this. Again, it's, I think anybody in this room, given the technical capabilities of this crowd, 2 hours on the weekend would be enough to get you to the point where you have something that you could send off to be manufactured. You spend 200 bucks, you'll get back a board, which for some reason I did not think to bring with me, but you get back a dev board that basically has a chip mounted in the center that is your design. It's got everybody else's designs on it as well, but it also has your design. And so you can get started really quickly. So Tiny Tapeout has been super successful. They've done 10 plus chips from 30 plus countries with 50 plus universities, done 1,500 plus designs, and over 5,000 different people have taped out. And some of them have been younger than our friend who was over here. So it is really accessible. And so we kind of had this thing where at the kind of end of 2022, we had this process where you could get a free tape out through Google, or you could give this company called eFabless 10K and get a tape out. And that's what Tiny Tape Out was using, because if you get your 10K and divide it by the number of people on it, it was about $200. And that was all manufactured at Skywater. Then Google decided it was going to stop funding that program. They had already funded quite a lot of chips. So they have no requirement to keep doing that. But you could still choose, if you had 10K, you could choose to get your chips manufactured. So Tiny Tape Out still meant you could do a $200 tape out because they were using Chip Ignite to do a tape out effectively on Skywater. And then eFabless was a VC-backed startup, and they decided to go under. This was at the beginning of this year, and that's Matt Venn, the designer behind Tiny Tape Out, which meant now Tiny Tape Out has a problem, because if eFabless goes away, they don't have a direct relationship with Skywater, and Skywater is probably not going to give them the type of pricing that eFabless was, and so Tiny Tape Out had no way to do silicon. But if you had noticed earlier, IHP had kind of come into the scene, and they were a foundry that was willing to offer this service. So in a very short period of time, Tiny Tape Out went, oh, well, I guess we're going to use IHP now for all our tape outs. And they were successful importing all their infrastructure to IHP, which was pretty amazing because they had about 200-ish projects they had to port. And they did it in about 2 weeks, is my understanding, which industry said was totally impossible. So Tiny Tape Out was able to live on through IHP. But what you may have noticed is I haven't really mentioned more about this GlobalFoundries 180 MCU, which is the one that's made here in Singapore. I did point out that they had done 80 designs that they sent off to be manufactured on this process that Google had funded, but eFabless had never actually had a program that let you buy more manufacturing runs on this. And while eFabless existed, it was very much a case of I didn't want to create a competing company, even though I believe that GF180 MCU is a much better first process technology for people to get started with, because it's a very cheap process technology and it's a very bare bones process technology. The IHP and Skywater technologies are a very boutique foundries. They're small volume and they have a lot of features, and every feature you add adds more cost. Whereas like GlobalFoundries is, I think, the 5th biggest silicon manufacturer in the world. And so they have a much better cost structure. So with eFabless disappearing and the world in turmoil in open source silicon, I had been kind of on a holiday for about a year after leaving Google. I kind of went to the whole, I guess I'll do it myself. And that's where wafer.space comes from. So wafer.space is a Singapore-based company that is manufacturing with GlobalFoundries in Singapore. So I really tried to make it possible so that you can make a product like an Arduino type product using your own custom silicon. So if you go to buy.wafer.space right now, I've got business cards here if you want them. For $7,000, you get basically 1,000 parts. And of those 1,000 parts, you get 20 millimeters of silicon, which is about enough to do a microcontroller like an Atmel that was on the early, Arduinos. Some crazy people seem to believe they can do even a low-speed embedded Linux-capable solution. And one of the cool things I'll tell you later, they seem to be more right than what industry seems to think. Then, if you just want a full wafer, I'm offering the wafer for $2,000. And then this is unpackaged die. So like, there's a little, that thing there going around. So that's what you get back for $7,000. It turns out most people have trouble dealing with that tiny little thing. And so for a limited time, for $8,500, we'll take that chip and mount it on a PCB using a thing called chip-on-board wire bonding. If you've ever had, like a PCB with a little black blob on it, that's what wire bonding is. And so my hope is, and I'm working with a bunch of PCB assembly houses so that they will offer PCB-A, which includes getting your chip mounted. So then I will get to stop doing this. But until that time, we've kind of got an option to allow you to get chips packaged. And because if you think about it, those are quite small. You can make a PCB that kind of looks like those old DIP chips, the dual inline with pins. And so that's kind of what the PCB option will be. So you'll be able to get your chip back and put it in your breadboard or put it in your own PCB and that type of thing. And so I like to think of this as trying to do for what places like PCBWay, Seed, JLPCB have done in the PCB space. I'm old enough to remember that PCBs used to be a call us for a quote was the only way to get a price for a PCB. And that's kind of the way the silicon industry is, except it's find somebody who's in the silicon industry to call us, and then maybe we'll sign 3 NDAs, and then we'll give you a quote. So this is trying to be transparent like that. And yeah, you get about 20 millimeters of silicon, and it's all manufactured here at Global Foundries in Singapore. The current timeline for the first run, you have until the 28th of November to purchase a slot, and then your final GDS needs to be in. GDS, if you're familiar with PCBs, is kind of like the Gerber of the silicon world. That needs to be in by the 3rd of December. And then if all goes well, they'll end up getting shipped back to you around the 15th of March. So about 3-ish months. And one of the really cool things is that Tiny Tapeout was able to get funding to port their infrastructure so that they can also support Global Foundries 180 MCU. And so they're in the process of doing that, and they'll be on the first run. And so they will be a customer of basically wafer.space. And if you know $7,000 is a smaller number than $10,000, that $10,000 used to only get you back, I think, about 100 chips. I'm getting you back 1,000 chips. So who knows what this price will end up being for the ones that go through Global Foundries. At the same time, one of the good things about open source is that when a VC company, back company goes under, all the things that's released as open source don't disappear. They still exist. And so a couple of people involved with eFabless decided to start Chip Foundry. And so Chip Foundry basically offers what eFabless used to offer. It's a little bit more expensive than what eFabless offer. And recently, my understanding is they managed to purchase all the old eFabless assets out from the bankruptcy proceeding and that type of thing. So that's Chip Foundry. And, Tiny Tapeout already supported Sky 130. And so now Tiny Tapeout has 3 different ways to effectively do a tapeout. And all of these should be below $200 to do a tapeout. And it also means that there are oops, now, there are options for open source silicon manufacturing in Asia, here in Singapore. In Europe, that's IHP, is based in Germany, and in the US, which is Skywater. And we all know that international trade has gotten a little bit more spicy lately. So this hopefully will mean that no matter where you are, you can access Tiny Tape Out. And here you can see the runs that are coming up. And here's the GF one. And as you can see, it's got a deadline of November 2025. You might figure that out is the deadline on the website for wafer.space. The other cool thing is that means that you can now use Tiny Tape Out for $200 to test some of your ideas before you commit to the 7K to do your own chip. And so it gives you a pathway to start off doing something that is, simple and easy, and then move to a position where maybe you're making a product out of it. And so I guess one of the questions is, what are people doing with GF180 MCU? So there's this group called OpenFA Oct. If you go to this URL, wafer.space/OpenFA 25, it will take you to it. And you can see these little chips in here, they're Global Foundries. They're like the little ones in there. And they built this flexible sensing thing that basically, like, you mount it on your finger and it can tell when you move your fingers around and by how much and all things like that. And that was all done on the Global Foundries process technology. Who here knows what a Z80 is? You may have learnt that the Z80 you can no longer buy anymore because they stopped manufacturing it. Some people who really love the Z80 went, well, screw that, we want to still have them. And so they taped out on Tiny Tape Out and proved that their design worked and is compatible with the Z80. And so now they're moving to wafer.space as a way to enable them to ship parts, right? And this is one of the really cool things. There's a software engineer who does embedded development who had never done any ASIC design 5 years ago, who was like, well, I've heard this RISC-V thing is pretty simple. I've always wanted to do my own hardware. He basically created his own RISC-V CPU and all the infrastructure needed to basically boot Linux. And he then took that and put that on Tiny Tape Out. He didn't know that industry says you can't put a Linux-capable CPU on 130 nanometers. That's a stupid thing to do. He also did not know that you definitely don't put a full Linux CPU in this type of space available in Tiny Tape Out, because like Tiny Tape Out is like 200, like that chip is a normal chip size. The reason it's that size is because that's what industry normally thinks a chip size is. And so that's how much space you're supposed to take up to do a Linux SoC, actually a lot more than that, but let's assume that that is. He put it in a much smaller percentage because Tiny Tape Out takes that space and divides it by 200. And as well, I've seen this boot. It's in the board that's sitting in my room back at the hotel. But my friend Carl in Chicago has actually put one online. So you can log into it remotely and see a piece of custom silicon that somebody did. And he just did it. He did it pretty much having never done this stuff before. He didn't do the sensible thing and like start with, maybe a counter or something like that. He decided he was going to do a whole system. And he succeeded. It boots Linux. And the really cool thing is he's an embedded engineer and he hates board support packages. If you ever worked with hardware from a vendor, you may have got a board support package that has a Linux kernel that's probably like 5 years out of date. This thing boots kernel.org Linux kernel. You go to kernel.org Linux and you download it and select the right options, it boots. You don't need any crazy vendor support package or anything. And so here's an example of a little counter If you're familiar with RTL, you can use a thing called LibreLane. There's your Verilog. You have your configuration, and you run LibreLane config.yaml, and out of that, you get GDS. That should be DRC clean by default. So in theory, you can send this off to get manufactured. And it's basically a one-line change to change it between whether you're targeting SkyWater or GlobalFoundries or AHP. So you can write this, and whatever is available for you, you can tape out on it without having to rework all your solution. I'm also planning to have a referral program because not everybody can afford $7,000. Basically, if you refer 7 people, you can choose to get $500 per referral. Whatever 7, that's $2,500, or you can get your own chip tape out. So that's kind of my plan to try and make it accessible to people. If you can convince a whole bunch of other people to buy a slot, you'll get a slot free, is kind of the idea behind this free program. And if you convince a lot of people and you don't want a slot, you can get some cash instead. This is still a work in progress, but that's where we hope to go. And a big thing is, these programs only continue to exist if you use them. And so if you're interested in seeing this type of stuff be accessible, you do need to get using it as soon as possible, because if you wait too long, it won't exist anymore because nobody used it. And the other cool thing is, unlike IHP or SkyWater, GlobalFoundries actually has a lot more technologies than just this one technology that they currently offer. And so if wafer.space is successful, we do see a pathway to expanding to these more technologies, because the foundries really just care about how many wafers they sell and how much they get per wafer. And so if we can start producing enough wafer volume, the finance people will be banging on the door saying, you better open source that PDK because we're losing money by not doing so, which is a much easier argument to have than an engineer kind of saying, it's good for the world for PDK to be released. I mean, it is, but the finance people are much more driven by money, and they tend to control whether or not you can do things like this. As well, it actually turns out the open source tools not only work with these old technologies, but work with much more modern technologies like the 12 nanometer technology that GlobalFoundries has. This is manufactured in the US, it's not manufactured here in Singapore. And Intel 16 is another technology. This is kind of 16 nanometers, so it's still a little bit behind where maybe the leading edge is. But there's definitely showing that maybe once you're successful and you've sold 100,000 of your chip on this older technology, you could move to a more modern technology. And this is $2,225 for 9 millimeters of silicon at this technology. So it's a little bit more expensive, so you better have a much better justification for it. So sign up to get notified, and I'm already 8 minutes over time. There's some kind of bonus slides. Who here's a student? A couple of you? One of the things that I think has kind of helped destroy a lot of the silicon industry is that older people basically grew up when technology was simpler. Nowadays, the first time somebody does a tape out is, in their PhD program, and they get one chance on some of the most advanced technology that human has ever created that is also super expensive. That is not a good process for getting interesting research out of people. You wanted them to screw up on technology where it costs you $200 a screw up, not 200K a screw up. And so I see a future where, the first time somebody does a tape out is in middle school. They get maybe another couple of tape outs in high school, because, it's only $200 to get a tape out done. You could do that as an after school club or something like that. In undergrad, you get a couple of more tape outs. So by the time you get to your PhD program, you've got 10 tape outs under your belt. If you've done something 10 times before, you're much more likely to want to do something interesting. And so I think that's really cool. And as I said, this openness has already shown that people as young as 4-year-olds or 9-year-old have succeeded in actually creating a silicon chip. I believe this one here basically outputs the name of the kid in sequential things. So it's not like the most advanced thing in the world, but they were successful and they got the chip back and it worked. And so there was also this program in Oklahoma around teaching high school teachers to do this. And at $200, it's not too bad. It's definitely something that, after school club could do. The big problem though is with ASICs. It takes about 3 months to find out whether your thing works or not. That's quite a long time, but it turns out there's this other thing called an FPGA, which does a fairly similar thing, except you can program it in a couple of minutes. We decided to put one in your USB port so you can have it with wherever you go. And so when you're stuck on a long flight, and you run out of videos to watch, you can just start hacking on it. And Sean over here was the sucker I got to actually make them. And the kind of deal was I wanted them to be cheap enough that I can give them out to people. Basically, I don't want it ending up in a drawer doing nothing. But if you come up to me and say you're actually going to use it and demonstrate that you're actually going to be happy, it's like I bought you a cup of coffee. So that's what I use these for. And, I'll give you one. These are fairly small FPGAs. If you want to play with bigger FPGAs, go to fpgas.online. In Chicago, a friend of mine has a bunch of FPGA boards connected to Raspberry Pis so that basically you can connect to the FPGA and program it. And if you screw it up, the thing will power cycle and go back to the state it was before. And so these are RT boards. They're quite powerful budget boards, but you can get them. Then if you want more info, this is basically a presentation of all my other presentations that I gave before 2024, so it doesn't include this. This presentation is accessible at this URL here. Hopefully it's rather memorable. One of the more advanced things that we're missing at the moment is a full PCI Express stack. It's definitely known that you can do PCI Express on 180 nanometers, probably PCI Express 1, not PCI Express 6, but having PCI Express on your chip, I think would definitely open up a lot more options than what you can do today. So this is kind of my plan on how to solve that. You can also find out more about why I did this and why I'm silly enough to do this on this AmpHour interview. There's a quick link to get to it because the AmpHour URL is too long. And I want to say, I kind of think of myself as a software engineer, but today I get to spend most of my time doing contracts and boring stuff so that you can do cool things like silicon. I spent 16 years at Google, which kind of what allows me to do wafer.space without having to accept outside investment. So when a VC doesn't agree with another VC, I'm not going to disappear because I have no connection to VCs. And yeah, I've been doing open source since 1994, and pretty much any argument that you tell me about why open silicon won't work, I heard about why open source won't work, including Bill Gates getting up in front of Congress and calling all these open source software developers are going to destroy the software industry. So, the software industry is definitely gone now. It's not very successful at all. So I'd like to see the same thing happen in the silicon industry. And this is my attempt to help it. So yeah, that's my talk. There's a couple of things floating around for you to look at. This thing here is a D flip-flop, and next to it is a inverter. They're both on the same scale, and you can see why an ASIC developer really wants an inverter and really doesn't want a flip-flop because of their relative size difference. And so that was really helpful. I've got FOMUs up here. There's some business cards floating around. There's a little pot of like the type of dies you get back floating around as well. Yeah, questions?
Do you have any open source testing solutions for chips?
I'm going to tell you a very quick story. A person on Twitter was talking about PCB design, and they were like, PCB design has gotten so cheap that it's much better for me to send off a board without spending multiple hours doing verification and get the board back and test it with the real thing in my hand now, instead of, because like when you don't have the real thing, it's much harder to figure out whether the thing will work. And so we're not there yet with silicon, but it's kind of a risk versus reward. If you're only paying $200 for it, it doesn't work. Oh, well. If you're paying $500 million for it, then maybe testing is a bit more important. And so like, that's the story I think we should think about, is like, the testing should be proportional to your risk. And so my hope is that like open source cores will get better to the point where, there are testing solutions as part of that are included. I don't get to play with any of them at the moment. I just get to, fill out contracts and sign NDAs and these type of boring things. If you go to the wafer.space Discord, you can talk to some people there who probably can tell you about things like design, scan chain flip-flop insertion, and well, design for testing as well, but like a lot of these type of topics. I don't think the current silicon industry has figured out the right level of trade-off at the moment. Maybe it has for how much things cost today to develop. But I think if a chip that costs $7,000 to develop instead of $100K, maybe your testing solution is going to be different. And so that's kind of like, I'm interested to see how this changes. And maybe the current silicon industry is right and we'll just reinvent all their current tools. But maybe we'll invent some things that the current industry doesn't do because the cost to benefit ratio is very different. There are some other questions over here.
Yeah, the question is about, I'm assuming you haven't spoken to TSMC.
So what I like to say is that TSMC has the least incentive for the current silicon industry to make a right turn and no longer care about the most advanced node. They are obviously very successful in what they do. They're making, a huge amount of money in the way the industry currently works. And, the other thing is open source software, how many people here still have a Windows computer? Because, open source didn't kill things like Windows or computer games or any of these type of things. Just because, open source is successful doesn't mean things like TSMC are necessarily going to need to do things differently if they still make money. Who knows? I do know it's getting a lot more expensive for them to do things, and maybe having a lot more customers than just Apple would be good for their bottom line. Who knows? I would listen to them rather than me, because they're the ones who can raise, the capital to build a silicon industry foundry. I don't need as much money, and I'm playing on much older nodes. But if I was TSMC, I'd be very interested in seeing a lot more people design silicon, because when they're successful, they probably will want an advanced chip, right? And so having more successful people in the space means that they have more customers, and more customers means they can charge more, right? So, but yeah, Global Foundries being a different silicon producer has more incentive to try things differently than, say, TSMC does.
I'm curious as to why Global Foundries decided to take on this. How did you convince them?
It turns out that they started turning up at events where people could name two foundries. They could name TSMC because everybody can name TSMC, and they could name Skywater. And they're like, Skywater makes 1,000th less wafers we are. They have one process technology. They're like a teeny company compared to us. Why the hell do people know about this tiny person over here and don't know about us, right? And it's because a lot of the things they're turning up to were software events, and software people like, I went to GitHub and searched for ASIC stuff, and the only thing I could find was Skywater stuff, right? So obviously they must be the biggest player after TSMC in the field, right? Who doesn't have a GitHub account, right? So I think that, I honestly don't know why they did it. I gave them the arguments, and they seemed to believe in it. And so we got that. I would have liked to have gotten as successful as the Skywater one was. But Google decided to change direction at that time and not continue to do that. So I'm now trying to do it myself instead of being a billion-dollar company doing it. And it's kind of a shame that, they aren't doing it, but, they don't actually owe us anything, right? They're a company, they need to make money doing whatever they want. I think I'm going to be much more successful in doing this in theory. All the stuff I'm doing, in theory, if people buy it, it's sustainable. It doesn't lose money. It's not like other programs out there that need government grants or anything like that to exist. Once this is up and running, it should be profitable and a pretty nice lifestyle business. So
I have two questions. So that's from an FPGA guy, to put things in perspective. So you have this $200 version with about 1,000 gates, right? So your $7,000 or $8,000, how equivalent is it from a gate point of view? And then the second question is more like Adnan was asking also, in one of these slides, you have some analog part. So do you do mixed thing, right?
Yes. So the first one, it depends. Anywhere between 100,000 and 1.2 million gates is the current estimate of stuff you can do. You could also think about it, well, if you get about 1,000 gates with tiny tape out, and tiny tape out has about 200 projects on there, then it's 200 times 1,000. As another way to think about it, there's obviously a bunch of overhead with dividing it up that you don't have to do. It also depends on what settings you use, how much memory you use. Like if you use memory blocks, the memory blocks are much more densely packed than just general transistors. So, how much can you fit on an FPGA? You've got a theoretical limit on what you can fit in the FPGA, but that doesn't really tell you what you can do with it, right? It just tells you how many random LUTs. And even then, have you ever succeeded in having a design where there's 100% utilization of the resources in FPGA? If you do, you're much smarter than I have. I think, Zobs, we got up to 98% on the FOMU at one point, 99. I don't know of any other FPGA architecture you can get that high. Your other question was analog. Analog may be a reason why you want to do an ASIC over an FPGA, because an FPGA can only do digital stuff, although there is a program by a group out of Columbia University called Mosbius, which is trying to build basically a analog FPGA. And they are currently in the process of trying to make that design work on wafer.space, because if they can make that work, they can then sell the parts to people in the education space for, maybe $100. Because, I don't know how hardware people are, but like the general rule of thumb is 3 times BOM cost. So if you've got a $100 product, your BOM should be about $30. If you can think about it, $7 out of a $30 BOM is a significant portion, but it's not all of it. And so you could produce a $100 product, 1,000 of them with this. And that's kind of like the target. And if you need analog stuff that you can't do on FPGAs, maybe this is a solution to that. Tiny Tape-Out does support analog on Skywater. I think they've finally got analog working on IHP. It will be a bit longer before they have analog support on Global Foundries, but we do want to get there. So at the moment, if you want to do a lot of analog stuff, I believe you have to go directly with wafer.space. But at some point, you'll be able to do analog test stuff with Tiny Tape-Out on Global Foundries as well.
We'll take one more question and then we'll move to the next speaker.
So my question is like maybe a boring operational one. So you showed us this timeline and it was like 9 months or something from initial like buy-in to getting your parts. So my question is that pipelined? Like is this process starting every month, or is it like, okay, either you get on this bus or you have to wait 9 months for the next bus?
So it's 4 months-ish. If you think about the GDS in, when you have to have design in is the beginning of December. They come back March. So it's December, January, February, and then a bit of slack. Initially, it depends on how much demand I have. If I have enough demand to run one a day, I will run one a day. If I have enough demand that I can only run once every 6 months, I'll only run once every 6 months. But I would like to see this happen weekly. At weekly, it totally changes the economics here, because at the moment, as you said, if your design is ready one day after the tape-out closes, you're now waiting another 3 months before you can send that off to be manufacturing. If they're going weekly, you're waiting 7 days. And talking to a bunch of companies, they're like, that would be a game changer for us, because if the moment we miss a deadline, our product is delayed by 6 months. And like these days, 6 months, that's infinite time. I'm a software engineer, 60 seconds is infinite time, but yeah. And so I hope as the price goes down and we get this type of thing, the number of people who want to do this will go up. Because if you think about it, the number of markets that can recoup the cost of $500 million worth of development, there's not that many markets that can do that. The number of markets where you can recoup a couple of $1,000, you can probably do that just selling, a niche guitar pedal to, people who only like things that are green, right? Like, and that's why 1,000 chips, right? Like I kind of think of it as like, if you get 1,000, 100 go into your first prototype that don't work, 100 go into your second prototype, which actually works, and then you've still got 500 left over to go to your first 500 early adopter things. And if you manage to sell out them, then you could just buy another slot and get another 1,000 chips. It's you shouldn't think about it like as a prototyping service. It gets you 1,000 chips. If that's what you need for manufacturing, it's a manufacturing service for you. Just like, PCBs. You can start with a smaller number and then ramp it up.
Yeah, thanks. And my other question was going to be on the Tiny Tape-Out thing where you have hundreds of designs. How does the I/O work there? Like,
if you've dealt with Arduino, you might be familiar with a thing called a pin mux that basically maps the various different peripherals you have to the different pins. They basically have a really interesting version of that. that allows them to match, 200 different projects and match them to different pins. There's a YouTube video from Sylvain. If you go to Tiny Tapeout YouTube channel, they will link you to how this was designed. And the great thing is that, like, because it's all open, you can actually go and look at the exact stuff they did. And if you think you can do better, I'm actually sure they would love, for you to prove it, right? Like, if you can use half as much resources to do it, they can fit a lot more things on there, so the price goes down, so everybody's happy, right? Like, and it's already gone through a couple of iterations. When they first started, it was a giant scan chain that allowed them to get the data in and out. That ran about 100 kilohertz or something was the maximum speed of the signal, because if you can imagine, like 500 things is quite slow. When Sylvain redesigned it, I think they can do 100-ish megahertz type signals now. With analog, I mean, the bandwidth is effectively thing. And one of the cool things is IHP has these things called silicon germanium transistors. You can't use them with Tiny Tapeout, but like with IHP directly, a bunch of people have done some things like a 300 gigahertz transpedance amplifier and using entirely open source tools and open source PDK. I have no idea about what half those words mean, but it says 300 gigahertz there, which seems pretty fast to me. So, it will be interesting to see whether it works. But the group that did it was, I believe, in Bangladesh. And the reason they did it was because they need it for the thing they're developing. And the proprietary tooling vendors were like, we can't even find Bangladesh on a map. Why the hell are you talking to us type thing, right? Like, especially a startup in Bangladesh, right? Like, it wasn't like it's a big Bangladesh. It was like 5 guys who wanted to do something AI related or something. And like, we need 300 gigahertz for this. And these people won't talk to us. Well, like, we will use the open source tools to do this because we have no other option. And hopefully it works. I have no idea if it will. My kind of part of this is to basically let you do it cheaply and see what cool things you do.